Could you measure the X, Y and Z individually, or is that not an option?
There's two problems with that. One is that the big change is due to the distance up and down below you, which primarily will affect the z-axis, at least when you're flat. You just end up having to solve exactly the same problem for the z-axis. What this does is it basically just tweaks each of the weights of the x, y and z-axis until it sees a nice flat curve in the kind of previous points. Now, there is a kind of classic signal processing approach to this problem, which would be to use a low-pass filter. If you're trying to solve a problem we're trying to solve here, which is find position in a swimming pool, you want to find what the position is now. And with a low-pass filter, it's got a kind of inherent delay. And to actually build a low-pass filter that filters out things that are on the order of kind of seconds, so a stroke, you'll be typically doing sort of one stroke per second or so. Your low-pass filter is going to give you a sort of 2 or 3 second delay, which for a fast swimmer, that's got from 10 meters or something, on a push-off or a dive, that's got from a long way. So you can't really use classic signal processing approach. So this is why we use this kind of approach, which basically kind of shuffles each one. It's a kind of gradient descent. It shuffles each weight and it says, did that make it better or worse? And if it makes it better, it accepts it.
Smartphones have accelerometers in, don't they? Presumably you could sync these up and work out what orientation the phone is.
So yeah, you can do that. The problem I found when I was doing that is that the timing of sensors on phones, or at least the timing of sensors on the model of phone I had was not the same. So the magnetometer was sending out signals at a different time to the accelerometer. And when you put that into the algorithm to kind of correct for this, it just didn't work because you could never get them synchronized, and neither sensor was sending things at bang on 200 times a second or something. They were all kind of a bit stuttery, and it just didn't work correcting it that way.
Just not precise enough, presumably.
Yeah, the chip's in an accelerometer chip that's in a smartphone. That'll cost sort of $1 or something, very little amount of money. The key thing to understand with this is where the error is. So the error is in when you're taking the magnitude, you've got an X and a Y and a Z, and you know that those are off by a little bit. Initially, you record the kind of signature of a pool, I've called it, the shape that that pool gives out if you swam flat across it. That's not really used in a correction algorithm, that's only used for matching where you are in the pool. When I am kind of filtering out the noise here, the noise that's from side to side movement, all I'm actually using is the previous, I think, 4 seconds of swimming. The reason for that is that this noise is very much dependent on when you actually did each stroke. So you can't really filter it out purely using the pool signature or using any kind of known things about the error in the magnetometer and stuff. So there are quite a lot of algorithms for correcting for error in magnetometers. But the problem with those is they all assume that the source of the error is static and you're trying to correct for a static source of error. Whereas what we're trying to do really is detect a particular source of error which changes all the time, so the effect of it changes all the time. So I mean, all these kind of classic algorithms for doing it just don't work when you stick someone in a swimming pool where there's loads of magnetic error around. So on these two graphs here, you can see, here is the before graph, this is showing all the magnetic error, and this actually has quite a bad case of magnetic error, so it's really big. And actually, once you've processed that out, it actually takes the most smooth weighting of all these sensors, and here you can see this is a really smooth graph here. You can really see the shape of the pool signature, which I showed before, in that graph, and that's from a real swimmer. That's actually from me swimming along a pool.
So that's the corrected, it's not just a flat signature of the pool?
That's the corrected signature that was recorded from me swimming along. There's the basic things that you can do which people will obviously want, like timing swimming and stuff like that, which is very easy, but then you can do much more complex feedback. So we've actually sort of started thinking a bit about using music which is actually controlled by the swimming, so it kind of responds to how you're swimming and perhaps responds to kind of a rhythm of your swimming and the kind of nature of your swimming, how good your swimming is, and looking at, can you measure things like that? And can you, once you have measured them, can you actually kind of give people useful responses?
And is that, I mean, would that be all sorts of different possibilities, not just rhythm of the music, you know, tempo of the music? Would that be kind of the style or the melody? Would you get sad music if you're not doing so well? Or?
If you've got a smartphone attached to you and you have some way of getting audio to your ears, you've got waterproof headphones on, or you've got some way of getting kind of rhythm to you through vibrations, you've got a really powerful computing device. So yeah, you can really do things that respond to people in very nuanced and new ways. The focus now is taking this kind of technology we've built, this technology for magnetic sensing. I've also built some stuff to do with, as well as sensing the fact that someone's doing a stroke. So saying you did one pull of front crawl, or you did one stroke cycle of breaststroke. It's also looking at how you did that, so how well you did that, or what particular kind of stylistic elements of that there are, because people swim in very different ways, and some of them are more or less efficient than others.